Hi ladies, this is lesson 8.1. This is about the Pythagorean theorem and its converse. So we're going to look at a couple examples using the Pythagorean theorem and the converse of the Pythagorean theorem, which remember the converse just switches the if and the then part of a theorem. So first let's start by looking at triangles because the Pythagorean theorem deals with right triangles, only with right triangles. So we're going to look at this figure on the left, and we're going to write three unique similarity statements for the triangles in this figure. So the first thing you should notice is that there are three triangles. Here's one triangle. Here's another triangle. And this big one is the third triangle. So with those three triangles, we're looking to see which one is congruent, or which one is similar, rather, to triangle BDC. So we're going to focus on this triangle, BDC. So with similarity statements between triangles, remember that you have to have three congruent angles. That's one similarity shortcut. Let's look at all of the angles that measure x. Here's an angle that measures x, and here's an angle that measures x. And then here's an angle that measures y, and here's an angle that measures y. So we're going to start by matching up those angles. So the angle that correlates to angle B would be in this triangle, angle C. The angle that correlates to angle D in this triangle is D. And the angle that correlates to angle C in the first triangle is angle A. So that's one similarity statement. Now, before we get to the next two, I'm going to jump down to this question. What is the sum of x plus y? Well, if you look at either one of these triangles, let's just look at the smaller one. This is a right triangle. Remember that a triangle has to sum to 180 degrees. And then angle D is 90 degrees. So x plus y has to also be 90 degrees. And we don't know the exact measure of x and the exact measure of y, but what we do know is that they add up to 90 degrees. So if they add up to 90 degrees, that means that this angle is 90 degrees. So in this second similarity statement, again, we're looking at this triangle BDC. Where angle B is x degrees, angle D is 90 degrees, and angle C is y degrees. So we can write a second similarity statement with that dealing with this large triangle. So in the large triangle, the angle that correlates to B is also B. The angle that correlates to D is the 90-degree angle, so that's C. And then lastly, the angle that correlates to C, which is y degrees, is A. Okay, and then our last similarity statement deals with the triangle on the right. Now we already said that this triangle and this triangle, we already said that that is similar. So let's write a similarity statement for the big one. And again, you know that this angle is 90 degrees because x plus y have to add up to 90 degrees. So angle B, CA, that's going to be similar. That's the blue triangle. That's going to be similar to the green triangle, but we have to make sure that we put it in the right order. So angle B, which is x degrees, correlates with angle C, which is x degrees. Angle C, which is 90 degrees, correlates to angle D, right here, which is 90 degrees. So C, D, and angle A, which is y degrees, correlates with angle A, which is y degrees. So with those three similarity statements, now we can solve for missing pieces. Because we know the triangles are similar, we can use proportions of similar triangles to find this height, h. So let's think of our proportions, and it's going to help if you kind of visualize this triangle in the same order. So let's just shift this triangle that also involves h. So just imagine rotating that triangle on the right 90 degrees so that your corresponding parts in your pictures match up. You don't have to do it that way. You can look at your similarity statements, but it's just a little bit easier to visualize if we rotate that second triangle. So we know that R is 9 centimeters, and we know that T is 25, which this here is T. So let's write a similarity statement. 9 to h here, 9 to h, those bases are going to be equivalent to the ratio h to 25. Now we can solve for h by taking 9 times 25 and h times h, which is h squared. Now we need to take the square root of both sides. So the square root of 9 times 25, which is 225, is 15. And that's our value for h using proportions. Okay, now this is important. This example here, this review was important because in the Pythagorean theorem, we are working specifically with right triangles like we did in this example. But before we do that, we have a few vocabulary terms. So in this diagram on the right, this is your hypotenuse. And so in a right triangle, the hypotenuse is the opposite side of the right angle. The leg of a right triangle is either one of the sides that make up the right angle in a right triangle. Now, so far we've been working with conjectures because in this class we haven't been doing proofs, but a theorem is a conjecture that's been proven. So our conjectures are just based on observations, but a theorem actually has proof. So again, in this lesson, we're looking at the Pythagorean theorem, which you may be familiar with, but it's specifically for right triangles, and it's the relationship between the legs and the hypotenuse, the length of the legs and the length of the hypotenuse of the triangle. And that relationship is a squared plus b squared equals c squared, where a and b are legs and c is the hypotenuse. And then our last term is Pythagorean triples, and these are perfect integers that work in the Pythagorean theorem. So there are a bunch of examples in your book. I'll give you a couple now. 3, 4, 5 is a Pythagorean triple. 8, 15, 17 is a Pythagorean triple. So both of those examples, 3 squared plus 4 squared equals 5 squared, that works in the Pythagorean theorem. And then 8, 15, 17, 8 squared plus 15 squared equals 17 squared. Those are both true statements, which makes those Pythagorean triples. All right, let's look at a couple examples here. So we're going to use the Pythagorean theorem to solve for the missing side lengths. Again, the Pythagorean theorem is a squared plus b squared equals c squared, where a and b are legs, so the legs form the right angle, and c is the hypotenuse. So in this example, 8 is a leg, 3 is a leg, and c is the hypotenuse. So 8 squared plus 3 squared equals c squared. So 64 plus 9 equals c squared. So 73 equals the square root of 73 equals c. So you can leave it as the square root of 73 if you'd like. Just make sure that you simplify any radicals that you have, or you can calculate it out. And if you calculate it out, you get about 8.5 feet. All right, in the second example, here we don't have one of the legs. This is missing, but we do have our hypotenuse. So we can still use the Pythagorean theorem. One leg squared plus the other leg squared equals the hypotenuse squared. So 196 plus b squared equals 400. You can subtract 196 from both sides, and you get b squared equals 204. Then you need to take the square root of both sides to solve for b, and you get b is approximately equal to 14.3 feet. Right, now the Pythagorean theorem says if there is a right triangle, then a squared plus b squared equals c squared. Now remember what a converse is. The converse switches the if and the then part of the theorem. So this is now the then part, and this is the if part of the converse. So if a squared plus b squared equals c squared, then the triangle is a right triangle. So let's look at the converse for an example. So here we have a steel pole that measures 150 centimeters. It's on the ground The contractors are ready to put the cement around it to seal it in place. But first we want to make sure it's perpendicular. So the contractor has measured the distance from the top of the pole to the base of the pole on the ground, and we're wondering if it's perpendicular to the ground. So is this a 90-degree angle? That's what perpendicular means. Well, if it's a 90-degree angle, then a squared plus b squared will equal c squared. So we want to check 80 squared plus 150 squared. We want to make sure that equals 180 squared. If that's true, then it is perpendicular. So 80 squared is 6,400. 150 squared is 225,500, 22,500. And that should equal 32,400. Well, 28,900 does not equal 32,400. So therefore, since the Pythagorean theorem does not hold true, this is not perpendicular. So it's not a right triangle. So pole is not perpendicular to the ground. All right, let's look at one more example. So in this example, if the radius of a circle, we're looking for the radius of a circle that circumscribes a square that has a perimeter of 16 centimeters. So here's our square. In a square, we know that all sides are congruent. And all of these sides added up together are 16. So we know that one of these sides is 4 centimeters. And the second part of this is that we're looking for a circle that circumscribes this square. So a circle that circumscribes this square will go around the outside of the square. It'll touch all corners of the square. All right, now we're looking for the radius of the circle. So the radius goes from the center of the circle to the outside edge. So we want to go from the center of the circle to the outside edge of the circle. And specifically, we're going to go somewhere that touches the square because we only have measurements for the square. Now we don't know this length right here that goes from the center of the square to the corner of the square, but pretty easily using the Pythagorean theorem, we could find this whole diagonal of the square. So the diagonal of the square is the hypotenuse of a right triangle. And this right triangle has two legs that are both 4 centimeters. So a squared plus b squared equals c squared. So the square root of 32 is approximately 5.7. Now we're not looking for the diameter of the square, we're only looking for the radius. We're not looking for the diameter of the circle, we're only looking for the radius. So the relationship between diameter and radius is that the diameter is twice as big as the radius. So if we know the diameter is 5.7 centimeters, that's equal to 2 times the radius. So we can divide both sides by 2. 5.7 divided by 2 is about 2.85. So the radius of our circle is about 2.85 centimeters. So please jot down any questions that you have and we can go over them next time I see you in class. Thanks.